Hello, welcome to section 6.5, solving polynomial equations. Factor polynomials. For any number of terms, we're going to check for a greatest common factor. It's one of the first things you're going to want to do in any factoring polynomial problem. But then there are techniques for factoring polynomials that are more in-depth. First, for two terms, you check for the difference of two squares. In other words, a squared minus b squared will be equal to a plus b times a minus b. The sum of two cubes, a cubed plus b cubed, equals a plus b times the quantity a squared minus ab plus b squared. And then the difference of two cubes, a cubed minus b cubed, which is equal to a minus b times a squared plus ab plus b squared. For three terms, we check for perfect square trinomials. For example, a squared plus 2ab plus b squared equals a plus b quantity squared. A squared minus 2ab plus b squared equals a minus b quantity squared. And then general trinomials, ac x squared plus the quantity ad plus bc in parentheses times x plus bd equals ax plus b times the quantity cx plus d. So in essence, we're looking at a foiling approach, taking ax plus b times cx plus d and splitting it up into these general trinomial terms, first, second, and then third term. For four or more terms, we check for grouping. Ax plus bx plus ay plus by equals x times the quantity a plus b plus y times the quantity a plus b, which is then equal to, once again, two binomials multiplied, in this case a plus b times the quantity x plus y. We're going to talk about how all of these techniques for factoring apply in the examples and exercises that follow. Starting off, first example, factor 24x squared minus 42x minus 45. So we're going to first factor out the GCF to get 24x squared minus 42x minus 45 equal to the following. 3, which is in fact the GCF, factored out of this original trinomial, gives us parentheses 8x squared. In other words, 3 times 8x squared is 24x squared if we kind of go through and multiply or distribute. And then dividing a 3 out of negative 42 gives us negative 14x. And factoring out a 3 out of negative 45 gives us negative 15. To find the coefficients of the x terms, you must find two numbers whose product is 8 times negative 15, which is negative 120, and whose sum is negative 14. The two coefficients must be negative 20 and 6. Negative 20 plus 6 is negative 14. Negative 20 times 6 is negative 120. Rewrite the expression using negative 20x and 6x and factor by grouping. Okay, this method is also referred to as split middle term. And as you can see, they rewrote the problem. 8x squared minus the 20x, we'll circle that from here, plus 6x, circle that from there, minus 15. From here we can factor out a GCF from each binomial, particularly 4x from 8x squared and negative 20x, which I'm going to make even more clear here by factoring by grouping with parentheses around the first two terms and the second two terms. So continuing, again, just looking at these two terms, we could factor out a 4x, and that leaves us then with 2x. 4x times 2x is 8x squared. Factoring out a 4x out of negative 20x leaves us with negative 5. Similarly with these two terms, although different GCF as we can see, but similarly we factor it out, we have, in this case, 3. You are left then with 2x and then minus 5. Turns out that these two quantities are identical. Because they're identical, we could say that as a factored form, 2x minus 5 is part of that, but so is 4x plus 3. You put it all together, you have 4x plus 3 times the quantity 2x minus 5. Now recall that at the very beginning of all of this, we factored out a GCF of 3. Okay, that particular GCF that we factored out has to be then included in our final answer here, so that when it's all said and done, putting it all together, we have 3 times the quantity, 4x plus 3 times the quantity, 2x minus 5. That is the final factored form of this problem. Let's move on to the exercises. So factor completely. If the polynomial is not factorable, we're going to write prime. So, as we look at this problem, 14x squared, y squared, plus 42x y cubed, we can initially consider, just like the last problem, if in fact there happens to be a GCF. Let's go ahead and write this down. So for our purposes here, it is hopefully obvious that we do in fact have a GCF of 14. So in writing the GCF, that's just part of technically the full GCF. We're going to go ahead and also consider, though, the variables that are involved here, particularly the x and the y, x to the, in this case, firsts in this particular term, and x to the second in this particular term. But the x to the first is the one to really highlight first, because that is the exponent that is, well, smaller than the other. So we're going to consider x, not x squared, part of our GCF. In a very similar way, we're going to look at the other variable y, and notice, well, the smaller of the two variable exponents is 2. So as we put it all together here, y to the second, so 14xy to the second is your full GCF. Okay, so when it comes to then writing down our factored form here, 14 xy squared times the quantity, and we're literally going to divide 14x squared y squared by 14x y squared. 14 divided by 14 is just 1. No need to write that. X squared divided by x to the first. X squared divided by x to the first. Because the bases are the same, we simply subtract the exponents. So that just becomes x. Y squared divided by y squared is just 1. No need to write that. So that's my first term in the parentheses. The second term, if I take 42 divided by 14, I get 3. And then if I take x divided by x, we get 1. And then y cubed divided by y squared, well, subtract your exponents, 3 minus 2, you get 1. And therefore, y is the last part of that binomial in the parentheses. Your final answer, completely factored, 14xy squared times the quantity x plus 3y. Okay, so that's factoring out a GCF. Let's take a look at number 3. Number 3, we have ourselves a quadratic trinomial, 2x squared plus 18x plus 16. Now, as we've attempted to pull out of every single polynomial thus far, if it in fact exists, look for a GCF and pull it out, or factor it out. It may or may not be clear or obvious here, but there is a GCF of 2. In other words, 2 goes into 2, 18, and 16. And there's really no other common factor that can be factored out, So we'll stick with that. Factor out a 2, and then you're left with x to the second. 2x squared divided by 2 gives us x squared. 18x divided by 2, we're looking at plus 9x. And then lastly, 16 divided by 2, of course, 8. So this is our quadratic one-step simplified. We still have more to do, possibly, if in fact x squared plus 9x plus 8 is factorable. Turns out it is. So I'll work down below here. And in this instance, I'm going to just simply think of two numbers that multiply to give us 8 and add to give us 9. Similar to the original example when we looked at negative 120 and negative 14 as the product and sum. In this case, my product is 8, my sum is 9. And those two numbers, as I put my x's in the right spots there, those two numbers are 8 and 1. There is no need to split the middle term or go through the grouping like we saw in the example, because I can simply put in the two numbers 8 and 1. 8 times 1 is 8. 8 plus 1 is 9. Final answer, completely factored. 2 times the quantity x plus 8 times the quantity x plus 1. Let's move on. The next example that I think we should take a look at is example 4. X to the fourth minus 1. So clearly this is a higher level function of degree 4. We need to consider, like the problem or technique specifically that we observed at the very beginning, a squared minus b squared equals a plus b times a minus b. Although it doesn't have technically a perfect square, it is a perfect fourth. In other words, what number times itself 4 times gives you 1, but also what variable times itself 4 times gives you x to the fourth. And because it is in fact a perfect fourth, in other words, x times x times x times x is x to the fourth, and 1 times 1 times 1 times 1 is 1, we can actually identify this as a version of a perfect square. In other words, it's a squared squared. Here's how this is going to work. When we set up the factoring, we think of, okay, well, what is x squared times x squared going to give us? Well, x squared times x squared is in fact x to the fourth. So that does in fact work as far as our first two terms. Our second two terms, well, because 1 is a perfect square or perfect fourth, turns out that 1 times negative 1 is negative 1. And we are missing a middle term, so the signs are perfectly good. 1 minus 1 is 0. 1 times negative 1 is negative 1. Now if we were to FOIL this, as really we could have done on number 3 to check our math, if we were to FOIL this, we in fact get x to the fourth first, negative x squared outside, positive x squared inside, adding to 0. And then last, 1 times negative 1, negative 1. So this is a version of the difference of squares formula, but instead of using just x, we have x squared. And as you see, it works out perfectly fine. We're not done. And the reason we're not done is because x squared minus 1 is yet another difference of two squares. So I'm going to rewrite x squared plus 1, and I'm going to set myself up for the factoring of x squared minus 1. In other words, x and x plus 1 minus 1. 1 times negative 1 is negative 1. 1 minus 1 is 0. So that in fact, right here, is your final answer. You cannot do anything more to this problem. X squared plus 1 is not a difference, but a sum of two squares. And that's not a technique that's discussed up at the top. X squared minus 1 is, and therefore that is your final answer in full.